Jai Hind everyone. I am Krishna Gupta. I am assistant professor in Electronics and Communication Engineering Department in Ajay Kumar Garg Engineering College. This is lecture 3 of the subject Integrated Circuits. In this lecture, I am going to discuss voltage comparator and zero crossing detectors. So, firstly, we will discuss about operational amplifier as a voltage comparator. Then we will discuss about zero crossing detector. Now, before starting the topic voltage comparator, firstly we need to understand that how we can use operational amplifier in different modes, like in open loop mode and in closed loop mode. So you people had already studied the various op-amp circuits in which you had used negative feedback and positive feedback, right? So that is the closed loop configuration of op-amp. So as far as configuration is concerned, this operational amplifier, it can be used in two configuration. One is closed loop configuration and another one is open loop configuration. So closed loop configuration means there is some feedback. That feedback may be negative feedback, that feedback may be positive feedback. In open loop configuration of op-amp, there is no feedback. Operational amplifier, it will be in open loop configuration. So firstly, we need to understand that how this operational amplifier, it behaves in closed loop configuration and in open loop configuration. Then we'll see that one of the application of operational amplifier in open loop configuration is voltage comparator. So as far as closed loop configuration is concerned, in closed loop configuration, since we know that there are two input terminals, one is inverting input and another one is non-inverting input. If the output is connected to this negative input terminal, that is the inverting one, so we say that it forms the negative feedback. Similarly, if it is connected to the positive input terminal, then we say that it's a positive feedback. Fine. Now see, this negative feedback, it is utilized in amplifiers, and positive feedback, it is utilized in oscillators. So there are various applications of operational amplifier in closed loop configuration of op-amp. For example, adder circuit, subtractor circuit, integrator, differentiator, etc. So there are various applications we know that can be used in closed loop configuration of op-amp. But as far as open loop configuration of op-amp is concerned, this open loop configuration of op-amp, it is having limited applications. Open loop configuration of op-amp is having limited applications. The reason is, in open loop configuration of op-amp, the output of the op-amp get saturated. So we need to understand that why this open loop configuration of op-amp, it gets saturated. For that, we need to understand one basic circuit, that is this one. In this operational amplifier, let's say V1 voltage is applied at the non-inverting terminal and V2 voltage is applied at the inverting terminal, and the output voltage is V0. Output voltage is V0. And if it is 741 IC, then it requires 12 supplies. One is positive, that is plus VCC, and another one is negative supply, that is minus VCC. Fine. So you can see that in this circuit there is no feedback path. Output is not connected to any input terminal. So we can say that this op-amp, it is in open loop configuration of op-amp. Now see, what will be the output voltage if V1 is applied at the non-inverting terminal and V2 is applied at the inverting terminal. So for that, let's say the open loop gain, since this circuit, this op-amp is in open loop configuration, let's say the open loop gain of this op-amp is AOL. So this AOL, open loop gain, it will be output voltage upon input differential voltage. Input differential voltage, because this op-amp is a difference amplifier. So input differential voltage, it will be V1 minus V2. And we know that this open loop gain of op-amp, it is very high. It is very high because it is a multi-stage amplifier. So if we are taking 741 IC, that is one of the very popular op-amp IC, the open loop gain, it is 10 to the power 5 to 10 to the power 6. The open loop gain for 741 IC, it is around 10 to the power 5 to 10 to the power 6. And if the input voltage is 1 millivolt, I am just taking one example. If the input voltage, it is 1 millivolt, and let's take this AOL, that is the open loop gain, it is 10 to the power 5. Then what will be the output voltage? So we can calculate 10 to the power 5 into 1 millivolt. This V0 will be 10 to the power 5 into 1 millivolt, that is 10 to the power minus 3 volt, that is equal to 100 volt. So from this equation, we are getting that the output voltage of this open loop configuration of op-amp, it is 100 volt if V1 minus V2 is 1 millivolt, and if we take gain is equal to 10 to the power 5. And we know that in general, for example, 741 IC, we normally give maximum plus minus 15 volt, right? And the output voltage which we are getting is 100 volt. So it cannot happen because the output will not cross the supply voltage. Output will not cross the supply voltage. It means that when we apply 1 millivolt signal at the input, and let's take supply voltage plus minus 15 volt, then the output voltage will starts increasing, and it will maximum go to the plus 15 or minus 15 volt. In practical cases, it will not go exactly plus 15 volt, it will be less than 15 volt. That is called saturated voltage. That is called saturated voltage. It means that the output voltage V0, it can be at plus Vsat, and it can also be at minus Vsat, plus Vsat and minus Vsat. Now the next question is, when will the output of this open loop op-amp will be at plus Vsat, and when it will be at minus Vsat? So it's very simple. The output of the op-amp, it will be at plus Vsat if the voltage at the non-inverting terminal is greater than the inverting terminal voltage. That means the positive terminal voltage is greater than negative input terminal voltage, then output will be at plus Vsat. Otherwise, it will be at minus Vsat. So it means that when there is no feedback path in the operational amplifier, then because of the high open loop gain, the output of the op-amp, it gets saturated, and it will get saturated to one of the values, either it will be plus Vsat or minus Vsat, depending upon which voltage is greater at the input terminal. Fine. So sometimes we say that this open loop configuration of op-amp, it is having digital output because it is giving only two values, plus Vsat and minus Vsat. And when we draw the transfer characteristics of this operational amplifier, from there we can understand from the transfer characteristics. When we draw the transfer characteristics at the x-axis, it is input voltage, that is the input differential voltage VID, and at y-axis it is output voltage V0. So when VID increases in the positive direction, then V0 will increase, it will increase, and after a certain voltage it will get saturated. That value is plus Vsat. Fine. Because since the output voltage will get constant, if the output voltage is get constant, that means that output is saturated. Fine. Similarly, in the negative direction also, we can draw this graph in the negative direction also. in the negative direction, the maximum value that the op-amp can go, it will be minus Vset. So from here we can see that this particular region, this is the linear region of op-amp, and op-amp works as an amplifier in this particular region, right? And in this particular region where we are getting the output voltage plus Vset and minus Vset, we can say that the op-amp output of the op-amp is saturated. Fine. Now we need to understand that where this open loop configuration of op-amp is used, because closed loop configuration is having many applications in inverting configuration as well as in non-inverting configuration. In negative feedback, in positive feedback, in both, there are various applications. Fine. Like you can use you can use negative feedback in various circuits, right? Integrator, differentiators, and positive feedback, it can be utilized in oscillators. But open loop configuration of op-amp, it is basically used in voltage comparator. It compares two voltages, two input voltages. So coming to that topic, voltage comparator. This is one of the application of open loop configuration of op-amp. So as the name suggests, voltage comparator, it compares the input voltage signal with a reference voltage, right? Or we can say that it compares two input voltages. One is your input signal, one is the input signal Vin that is applied at one of the input terminal, that may be inverting input terminal, that may be non-inverting input terminal. This is the input signal. This may be sine wave also. This may be sine wave also. So this sine wave input signal is applied at one of the input terminal, and another voltage with which this sine wave is to be compared, that is the DC reference voltage, that is called V reference. So this Vin and V reference, these two signals are applied at two input terminals of op-amp. One is at a negative input terminal and another one is at non-inverting input terminal. And if the voltage at the non-inverting input terminal is more, then we will get plus Vset at the output, otherwise we will get minus Vset. Fine. Now coming to the types of voltage comparator, there are basically two types of voltage comparator. One is non-inverting voltage comparator, and another one is inverting voltage comparator. This is non-inverting voltage comparator. Right? So what is this non-inverting and inverting voltage comparator? If the input signal Vin, if it is applied at the non-inverting terminal and the reference voltage V reference is applied at the inverting terminal, then it is called non-inverting voltage comparator. So it means that in non-inverting voltage comparator, we are applying the input signal at the non-inverting terminal, and in inverting voltage comparator, we will apply the input signal at the inverting input terminal. That is the basic difference. So from here we can draw the input and output waveform of the non-inverting voltage comparator and inverting voltage comparator. So coming to non-inverting voltage comparator, So we can draw this circuit of non-inverting voltage comparator just by utilizing the open loop configuration of op-amp. So, we are having the input signal Vin. Let's say this input signal Vin is a sine wave. This is Vin, and this input signal Vin, it is applied at the non-inverting terminal, but although we can directly apply this input signal at the non-inverting terminal, or we can just connect a resistor also. I will discuss the function of this resistance R later, right? And another voltage, that is the reference voltage, right? So this Vn will be compared with that reference voltage, that is the DC voltage. So that DC voltage, that is the reference voltage, it is applied at the inverting terminal again through a resistance, let's say R. Fine. So this is non-inverting voltage comparator because Vin is applied at the non-inverting terminal, and there is no feedback path, and output voltage of op-amp is V0. Now there is one more thing. In order to protect the input stage of the operational amplifier, sometimes we connect two diodes, and these diodes are called clamp diodes. These diodes are called clamp diodes, and the function of these two diodes are to protect the input stage, because the input voltage of the op-amp, it will be set at plus 0.7 volt or minus 0.7 volt. By default we are considering this silicon diode, right? So it can protect the input of the op-amp from the very high input voltage, right? Although in some op-amps already there are input voltage protection circuitry already there, right, in some op-amps. So if there is a protection circuitry at the input in the op-amp, inside the op-amp, then there is no need to connect these diodes. Otherwise we need to connect it, these two diodes. Since because of these diodes the input voltage is clamped at either plus 0.7 volt or minus 0.7 volt, that's why these two diodes are called clamp diodes. And the function of this resistance R that is connected at the non-inverting terminal is to limit the current flowing through the diode, to protect the diode. And the another resistor that R is connected at the inverting terminal, the function is to just to minimize the offset problem. So these are the functions of these resistors R. Now coming to the input and output voltage waveform for this particular circuit. So one thing should be clear, since there is no feedback, there is open loop configuration, so at the output either we will get plus Vsat or we will get minus Vsat, plus Vsat or minus Vsat. So we will get plus Vsat if the voltage at the non-inverting terminal is more than inverting input terminal. Otherwise we will get minus Vsat. So keeping this in mind, we can draw the input and output voltage waveform. So we can see that the output voltage, it will be a pulse waveform, because that pulse will be having only two values, either plus Vsat or minus Vsat. So firstly draw the input signal, that is Vin versus T, Vin versus T, and this input signal we are taking it sine wave. So we can draw this sine wave, and this sine wave, it is applied at the non-inverting terminal, right? And this sine wave, magnitude of this sine wave, it will be compared with the inverting voltage, inverting terminal voltage, and at the inverting terminal we have applied a V reference voltage, that is the DC voltage. So obviously it will be a horizontal line, constant, and this is V reference that is applied at the inverting terminal. So I have drawn both the signals that has been applied at the inverting and non-inverting terminal. Now what will be the output voltage waveform. Output voltage waveform, that is V naught versus T. So to draw this V naught versus T graph, for that we can just draw the vertical line. From where? We can draw the vertical line from that point at which this V reference line is cutting the input signal V. So this one is the input signal V. Similarly, we can draw it. Now see, up to this portion, I am just marking it. Which voltage is greater? You can see that V reference is at upper side. V reference is at upper side. So V reference is greater than V in, and if V reference, if it is greater than V in, it means that inverting terminal voltage, it will be greater. So the output will be at minus V set. And after that, for this particular portion, now V in is greater than V reference. It means that the non-inverting terminal voltage is greater. So the output will switch from minus V set to plus V set. Similarly, you can draw the further waveforms. Just you have to see that which voltage is greater at which terminal, right? If the non-inverting terminal voltage is greater, then output will be at plus V set, otherwise it will be at minus V set. So it will be a pulse waveform. You can draw it easily. And one more thing, like voltage comparator has been divided into two parts, non-inverting and inverting. Now further, this non-inverting voltage in non-inverting voltage comparator, there can be two cases. The first case is V reference is positive, and the second case is V reference is negative. So once you understand the working of this circuit, you can draw the waveform of this non-inverting voltage comparator taking V reference negative. Fine. So because it's very easy, because we are at the output, we are just getting two values, either plus V set or minus V set. Fine. Now coming to the inverting voltage comparator. So in inverting voltage comparator, what we need to change the connection, what connections we are required to change? This input signal V in, it will be applied at the inverting terminal, and this V reference DC voltage, it will be applied at the non-inverting terminal. That is the inverting voltage comparator. Again, in inverting voltage comparator, there can be two cases. The first case is when reference voltage V reference, that is the DC voltage, is positive, and the second case is when V reference is negative. Fine. So you can draw the graph of the output, that will be again a pulse waveform for inverting voltage comparator. So this is the story of voltage comparator. Now next one is, what are the applications of this voltage comparator? One of the application of voltage comparator is zero crossing detector, that I am going to discuss. That is the next topic, zero crossing detector, right? So coming to the topic zero crossing detector, we will see that why it is called zero crossing detector, right? So we can easily draw the circuit of zero crossing detector just by taking V reference, that is the reference voltage, that is the DC quantity, is equal to 0. If we put V reference equal to 0 in inverting voltage comparator and non-inverting voltage comparator, it will become zero crossing detector. Again, in zero crossing detector, there can be two cases. The input signal is applied at the non-inverting terminal, and the second case is the input signal is applied at the inverting voltage comparator, right? At the input voltage at the input signal is applied at the inverting terminal, right? So taking one of the case, let's take the inverting case. It means that the input signal, it will be applied at the inverting terminal of op amp. So I am just roughly drawing this circuit just to make you understand. This input signal Vin, now it is directly applied at the inverting input terminal. Although we can connect a resistor also, like we have done it in voltage comparator, right? Now the reference voltage, it will be applied at the non-inverting terminal, but here in zero crossing detector we are taking this reference voltage is equal to 0. Reference voltage is equal to 0. So we can write it here, V reference is equal to 0. Now what will be the output voltage? Again you can see, this is open loop configuration of op-amp. Again the output of the op-amp will get saturated. It means that the output will be either at plus Vsat or at minus Vsat, depending upon which voltage, which terminal voltage is, which input terminal voltage is greater, right? Now we can draw the input output waveform for the zero crossing detector. So the first waveform is the input voltage V versus T. This is the sine wave, fine, and here V reference is 0. That's very much clear. Now what will be the output voltage waveform? Now here you can see that the sine wave at particular instant, it is crossing the x-axis. From there I am just drawing this vertical line, dotted vertical line, just to plot the graph more clearly, fine. Now see, for the positive half of the input signal, you can see that which voltage is greater, which input terminal voltage is greater. Obviously the inverting input terminal voltage is greater, because this sine wave is applied at the inverting input terminal. So it means that output voltage will be at minus Vsat. So just mark these two voltages, that is minus Vsat and plus Vsat. So the output voltage, it will be at plus Vsat. Similarly, when for the negative half of the input signal, for the negative half of the sine wave, you can see that which voltage is greater, which terminal voltage is greater. See, since 0 is greater than negative, so the non-inverting terminal voltage is greater, so the output will be at plus Vsat. Similarly, again it will switch from plus Vsat to minus Vsat. So you can see that whenever this input sine wave is crossing the 0 line, t axis, x-axis, the output is getting switched from minus Vsat to plus Vsat and plus Vsat to minus Vsat. So these are the points. I have mentioned these points through arrow. These are the points when the input sine wave is crossing from positive half to negative half to positive half, and you can see that at these particular instants the output is also switching from plus Vsat to minus Vsat and minus Vsat to plus Vsat. So you can understand that why it is called zero crossing detector. The reason is quite clear, because the instant at which the sine wave is crossing positive to negative, negative to positive, the output is getting switched. That's why it is called zero crossing detector. But in this zero crossing detector, there is one issue, and that is the disadvantage of this zero crossing detector. So to understand this disadvantage, see, we know that at the op-amp's input terminal there will be noise, obviously. If we are designing any circuit, electronic circuit, there will be noise voltage, and if due to that noise voltage, if this sine wave it gets corrupted, distorted, so it can happen that this sine wave, the shape of this sine wave, it will be like this. Just I am giving you one example. So you can see that here where I have circled, there are multiple crossings, and due to this multiple crossings, you can understand that there will be multiple switching at the output also. Multiple switching means plus Vset to minus Vset, minus Vset to plus Vset, but those switchings are false. Those switchings are undesirable. But it is happening here. It is happening here in zero crossing detector because of the noise present at the input of the op-amp. So this is one of the limitation of one of the disadvantage of zero crossing detector. That disadvantage is due to the noise present at the input terminal, there are false transitions at the output, false transitions at the output. In order to overcome this false transition, we use Schmitt trigger. Schmitt trigger, that is also called regenerative comparator. That is called regenerative comparator. The word comparator is there because in Schmitt trigger we use regenerative feedback. That regenerative feedback is also called positive feedback. And the concept of Schmitt trigger is, in Schmitt trigger circuit, two threshold voltage are generated. One is VUT, upper threshold level, and the another one is VLT, VUT and VLT. VUT is upper threshold and VLT is the lower threshold voltage. So just by generating these two threshold levels, this noise issue is addressed in Schmitt trigger. So in short, there is problem in zero crossing detector because of noise, and due to noise there are false transitions. So in order to avoid false transitions, we use Schmitt trigger. That is a different topic. Fine. So in this class, I have discussed about voltage comparator, open loop configuration of op-amp, its application. So one of the application of open loop configuration of op-amp is voltage comparator. So in voltage comparator, we have seen inverting voltage comparator and non-inverting voltage comparator. After that, the application of voltage comparator we have seen, that is the zero crossing detector. So there is, if we talk about the limitations of comparator, so one of the limitations of the comparator is compatibility of the output, because if we need to interface the output of the comparator to any IC, that IC, it may belong to different families. So let's take one of the popular logic families, TTL. So if we want to interface the output of the op-amp to TTL logic family, so compatibility issue arises, because in TTL normally it is 0 and 5 volt, the circuits work on 0 and 5 volt, and if the output of the comparator is different, so there is a compatibility issue. Although there is a issue, there is a solution also. In order to make TTL logic family compatible with the comparator, or we can say to make output of the comparator compatible with TTL logic family, we use some additional circuits called limiter circuit. Fine. So that is one of the issue, with the comparator compatibility issue, but we can resolve it just by using limiter circuit. Thank you.